In this lecture, we're going to learn about fractional numbers. And as we work with these numbers, I want you to keep in mind that any piece of data you work with in your C++ program is ultimately going to be stored in the form of ones and zeros in memory. Fractional numbers are also called floating types in technical terms. They are used to represent numbers with fractional parts in C++ and many other languages. And we have three types that we can use in C++. We have float, double, and long double. And the main difference is in the size they occupy in memory. A float takes 4 bytes, a double takes 8 bytes, and a long double takes 12 bytes typically. So as the size goes up, you can also notice that the precision goes up. So what is the precision? The precision is basically the number of bits you can represent with that type, starting from the number in front of the decimal point. So if we look at this number here, we can try and figure out its precision. So we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The precision here is 12. If we go back to our table, we're really not able to represent a number like this with a float. The smallest thing we can use to represent this number well is a double because the precision is 15 and it is more than what we need for this number, which is 12. One thing you should remember is that the number in front of the decimal point is also counted in when you are trying to figure out the precision for your floating point numbers in C++. So here we have an example of how we can declare and initialize floating point numbers in our C++ program. Number 1 is a really huge number, so you can guess that this is more than we can handle with the float. We're going to see how this is handled by our compiler. A double has a precision of 15, so we should expect to store more numbers than we did in a float. A long double should be able to handle this without a problem, because if we go back to our table here, our long double here should be able to handle this better than double, but it is possible that it is the same thing as double, depending on the compiler implementation. And if we try to print out the sizes here, we're going to see what the compiler gives us. We're going to do this when we try this in Visual Studio Code. Okay, and here we are trying to print out the precision of these numbers. We can use a special setting on our stream to control the maximum precision that we can see. Here you see that we are trying to show the precision for each number. There is a special setting we can put on stdc out to make it control the precision to a given number. Here we are using 20, and we're going to see that for number 1, this is going to be 7 digits. For number 2, it should be 15 digits or something close to that. The specifics are really dependent on the compiler implementation, and for long double, it should at least be the same as double or even more in some cases. Okay, here we want to see that we can also have narrowing errors if we try to store something big in a float, and a float can't really handle it. Here we have a number with a lot of digits, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we know that a float can only handle 7 digits. So this is probably going to give us a compiler error, as we've seen for braced initialization. If we use functional initialization, this problem is not going to be caught at compile time. So we're going to end up with a chunked piece of data, and we're going to see this when we play with this with Visual Studio Code. And another format we can use with floating points is that we can use scientific notation. And it is basically a way we can use a power of 10 multiplier to multiply with our floating point number. So for example here, number 5 is going to be this number, 192400023. We can use a floating point scientific notation to represent this. So what we're going to do, we're going to say 1.9, and we're going to multiply this with 10 to the power of 8. This is what this means. This 8 here means to multiply with 10 to the power of 8. And if we multiply with that, that basically means moving the decimal point 8 digits to the right. So we can go 1, 2, 3, 4, 5, 6, 7, 8, and it is going to end at these 3 here. And it is going to be basically the same number. Number 7 is also another one, and if we do this, we're going to pad with zeros after these 4, and we're going to end up at this same location as the 3, but it is going to be a 0. We're going to see about that in a minute. And number 8 is another floating point number, and we can use scientific notation to represent it, just like you see with number 9. We're basically going to have the same thing. When we have a minus in here, it means we're going to multiply with 10 to the power of minus 11. And this is going to give us a number below 1. Think 0.007 or something like that. So we're going to go 11 digits after the 0 here. And if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and the decimal point is going to go after 3. And we're going to basically end up with the same thing here. We're going to play with this in a minute, and you're going to see that all this makes sense. And don't forget that any piece of data we store in a computer is going to be ultimately represented by ones and zeros in memory. And for floating points, we don't use the number systems like we've done for integers. There is a special system that is used to do that, but it is a little bit complicated to cover in a course like this. I am just going to point you to it if you are interested, and when you are done with this course, you can come up and read on this. The main point is that any piece of data that you represent in your C++ program is going to be represented in terms of ones and zeros in the memory of your computer. Okay, there are a few things you can do with floating points that you can't really do with integers. For example, you can divide with 0. If you take a floating point number and divide that with 0, you're going to get what we call infinity. If the number is positive, you're going to get positive infinity. If the number is negative, you're going to get negative infinity. And you can take two floating point numbers that are zeros and divide them. And what you're going to get really is not a number. It's something called nan, which stands for not a number. And your program is going to not crash, but there are a few things you can't do with these things. For example, you can't add them up. You shouldn't really do this. It's probably going to end up bad for your program. Here we have a few examples. We have 3 numbers declared. They are doubles. They must be occupying 8 bytes in memory. Number 10 is initialized to 5.6. 11 is initialized to 0 because we are using braced initialization and we have nothing in here. And infinity here is the result of dividing a number by 0. So it's going to be positive infinity because number 10 is a positive number. If you go down, we're going to print number 10 divided by number 11, and we're going to say yields. We're going to put the result out. We're going to see that. Down here on the second line, you see that we are trying to add something to infinity, and this is also going to yield infinity because think of infinity as something super big. And if you add something small to something big, it's still going to be something big. Down here, you see that result equals number 11 divided by number 12, and these two are zeros, so we're going to end up with none, and that's what we're going to print in this statement here down to the bottom. Okay, you should really remember to put in the suffixes when you are initializing your floating point numbers. Otherwise, the default is going to be double. This is what we mean by this. You see this floating number, we have a suffix that is f to mean that it is a floating number. If you don't put that in, this is going to be interpreted as double, and the compiler is going to try and turn that into a float by chopping off things that can't really fit in a float. So to really make it clear that you are storing in a floating number, please put this f suffix here. For double, you don't need to put anything because it is the default assumed by the compiler. But for long double, you have to suffix this with L, just like this. So that's what we really mean here. We have seen that the precision for float isn't really enough for many of the computations we might want to do in our C++ applications. Okay, we have talked a lot about floating point numbers. Let's head to Visual Studio Code and actually play with them. Okay, here we are in our folder that is going to contain our project. The project is going to be called Fractional Numbers. So we're going to copy our files, go up a little bit, and put those in. And we're going to go up again and open this in Visual Studio Code. We're going to close whatever it is we have opened now. We're going to close folder, and we're going to open our project in Visual Studio Code. And we're going to do the usual and remove things we don't need in here. The first thing we want to do is to store a few floats in our program. We're going to declare and initialize a few floating point numbers. We have number 1, number 2, and number 3. And we want to make it clear that the sizes are what we expect. We are going to open a terminal window here, and we're going to build with GCC, run the task to build with GCC. The build is going to be successful. We're going to come to our terminal, click a little bit, and we're going to type dir. We're going to see that our program is in place. If we run it, we are going to see that size of float is 4. Size of double is 8, and size of long double is 16. This is what we expected. Another thing we can do is try and play with the precision of these numbers and see what we can really go away with. Okay, so we're going to actually put in a piece of code to play with this. We're going to add a setting to our STDC out stream so that we can control the precision. But for this to work, we need to bring in a library that is called IOmanip. So we're going to include that, IOmanip. And how do I know this? I usually consult the C++ standard library documentation. And you are not at a point where you can really understand it right now. So we're going to be putting in these things here and explaining them as we go. And I made a typo here. It is IOmanip. And you see that now this is recognized. Our program should compile. So we're going to try and build it so that we can try this out. We're going to build with GCC. The build is going to go through. We can run our program. We're going to do dir and clear and rooster to run. You see that things start to go off at 6. And if we count what we have here, it is 1, 2, 3, 4, 5, 6, 7. We can only represent 7 numbers accurately with a float. And after that, we're just going to have garbage because the computer can't really make sense of whatever we have after our 7 digits that we can legally represent with a float. So the precision for our floating point number here is 7. I really hope this makes sense. Let's check out number 2. We are using double, so precision should be around something like 15. So we are putting in a number 1 through 9, and we are starting over 0, 1, 2, 3, 4, 5 up to 0 again. If we look at what we have in the output here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, and here things start falling off after our 6 here. And if we count, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits. This is the precision we are having this compiler for doubles, 17. So it is something around 15, and we should expect to have something more than that, or at least the same thing as double with long double. So if we look at this, you see that it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are able to represent up to 20, and you can see that long double lives up to even the precision of 20 that we have set with STD set precision here. Okay, I really hope now that you have an idea about these precisions we have with our floating point types in C++ programs. Another thing I want you to see is what kind of narrowing errors we can get if we try to initialize with something that can't really be represented by a floating point number. And here we have a float, it is called number 4, and we are trying to put in something that is bigger than we can really fit in. It has more than 7 digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It is more than 7 digits. And we would expect to have a problem with this because we are using braced initialization. Let's try and build this with GCC. We're going to do that. And this is going to build successfully. So this is going to silently chop off our number. If we try to print it out, we're going to say stdc out number 4. And we're going to build again, run the task to build so that our changes are taken into effect. We're going to do dir and do rooster. And this is going to print our number. You're going to see that after the zeros, we have junk. Our number has been basically chopped off, and this is junk because we can't really represent this with the double. The 16 here has been chopped off because we can't basically represent this with the floating point number. If we change this to double, this is going to probably give us what we expect. So let's run again. Build with GCC. The build is going to be good. If we run the program, it is going to show us the same thing. Okay, this is a really good learning change. Why are we having the same results as before, even if we changed the type to double? Try to think about it. The reason is the suffix here is still saying F, and this is going to be stored as float in memory. So if we want this to really be treated like a double, we can take out the float here. And if we build again and run the application, now you're going to see that we see the 23. This is basically being correctly stored as a double. This is a really good thing you should keep in mind. If you don't put in your suffixes here, the number is going to be interpreted as double. By now, I hope you see that if you really try to put more than your floating point can handle, the number is going to be chopped off and only the precision that it can handle is going to be stored in. I hope this makes sense. And you see that the behavior for numbers is really different. We got a compiler error when we try to do narrowing conversion with integers, but now it is silently chopping off our number. If we try and use functional notation, I think we're going to get the same result. And change this back to a float and use float here. And if we build again, let's go to terminal, run task, use GCC. We're going to run this. Let's run rooster. And you see that we get the same results. Our 23 is chopped off here. We can also use the assignment notation here, just like we did with integers. And this is going to do exactly the same thing. It is going to chop off the 23 here, and we're going to have some garbage, which is 16 in this case. If we build again, the build is going to go through, and if we run, we're going to see a 16 here. Okay, narrowing conversions are something you should be aware of when storing your floating point numbers, and you should really remember to put in your suffixes here. Another thing we have seen that we should really play with is scientific notation. As the comment here says, what we have seen so far in floating point numbers is fixed notation. It is what we have here, but we can also use scientific notation, which is exactly what we described in the slides. And what we have here, for example, is E8. And it means that we are going to multiply this number here with 10 to the power of 8. If you go down here, we have number 9. So we have 3.498 and we have E minus 11. And what this is going to do is multiply with 10 to the power of minus 11. This is how I can represent this here. And we can print these numbers out to really play with them. To make a difference with what we have been doing before, we're going to do stdc out and put a dividing line here. This is one way we can do this. So we're going to do stdndl. We're going to build this. So we're going to run the task to build with GCC 10. The build is going to go through. If we do rooster, we're going to see that our number here, number 5 is what we expect. Number 6 is the same thing, but we used scientific notation to do this because we took this number and multiplied by 10 to the power of 8. Number 7 should be almost the same thing, but the lower 23 here is going to be chopped off because we haven't specified it. We're just multiplying with 10 to the power of 8. So that's why we have 0, 0 here. I hope that makes sense. And if you look at number 8, you see that we stored it like this without using scientific notation. We used fixed notation. But on the terminal, it's going to be printed out in scientific notation, and this may be pretty cool. The main usage for scientific notation is to make sense of numbers that are really huge. So the way you interpret this, you're going to move these numbers after the decimal points with 0 in front. And it's basically going to be like this. So if you count the zeros you have here, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is going to be directly after 3, and you're going to get the number here. This is what we mean. And number 9 was explicitly stored in using scientific notation, and you see that we have the same thing. You can play with these things and really make sense of them. And again, we didn't specify any suffix here, so these are going to be interpreted as doubles, but this is not a problem because they are doubles here. Okay, we are making some progress with this lecture, which is a little lengthy. The last thing we want to do is to play with infinity and none. We're going to put a message here to say what we want to do. And we're going to have number 10, which is going to be positive. We're going to have number 11, which is going to be 0. Number 12 is also going to be 0. If we take 10 and divide that with 11, we're going to get infinity because we are dividing a floating number with 0. If we try to print that out, we're going to get infinity, and we're going to get infinity for this result here because we are trying to add something small to infinity, which is something really big. And if we are trying to divide 0 with 0 in floating point, we're going to get what is called not a number. And if we print that out, we're going to see this in a minute. Let's build this with GCC. We're going to build successfully. Let's clear this out so that we don't have noise in here. And we're going to run rooster. And you see here, it says infinity and none, which is what we said here. And if we go down here, it is saying number 10 divided by number 11. And number 11 is 0. You see that here. It's going to yield infinity. If we add 5 to infinity, we're going to get infinity. And if we try to divide a 0 by a 0, we're going to get none, which is really a way to tell you that you're doing something wrong. You should really be careful. One other thing I want you to see is that if you turn this 5 into a minus 5 and build again, we're going to build with GCC and we're going to run this rooster. We're going to get minus infinity. So if you divide a positive number with 0, you're going to get positive infinity. And if you divide a negative number with infinity, you're going to get negative infinity. And this is what we see here. This is really all we set out to do in this lecture. I hope you found it interesting. And again, the big message is that any data type you're going to be handling in your C++ program is going to ultimately be stored as ones and zeros in memory. And we have learned about floating point numbers, float, double, and long, and they have these properties you see here, and you should use them with this in mind. Otherwise, you're going to have problems with your precision. Make sure you are using the correct precision that you need in your program. We are going to stop here in this lecture. The next one, we're going to try and learn about Booleans. Go ahead and finish up here and meet me there.